So what we do is when you create this kind of a dummy model, you do a lot of tests. You do a lot of it's called biofidelity test. Accurately you represent the biomechanics, and you try to achieve that. So this was one of the tests that we did. There is an impactor, there is a velocity given to it. We position the dummy in certain position, and you can see the inside of the head. You know, these are the face load cells. There is a foam here, there is skin and accelerometers and all that is there. And this little square pocket is our goal. So when we see our force, the probe force, the peak of that force has to be within this square pocket. And you can see how close we are to the upper boundary. So it's very easy to just fall out of it. So it requires a lot of engineering decision making, a lot of trial and error. We did so. Since you can see here, the impact is on the forehead. It's right here. It's right here. So the material properties of the skin and the foam below has a lot and lot of effect on this particular curve. So it has to be precisely tuned, and we cannot. And since it is a virtual model, for us it is very easy to use any random values, but we cannot do that. It has to have some kind of a physical relevance. The manufacturer should be able to make a material with that kind of a stiffness and material property. So very difficult, but it's achievable. We had entire team working on this particular project. Here you can see another biofidelity test scenario for the neck. So now you can see how. So we have a lot of vertebrae in our neck, right? It's a cervical spine, and how you can represent in the actual physical dummy. So there are a lot of rubber parts and the rigid plates and a lot of cables, and there is a joint here. There is a load cell here. We did the testing, and you can see here a lot of good results, a lot of bad results, right? So now earlier in this slide, what we saw that this peak has to be within this square, but in this kind of data, peak has to be within certain, but a loading and unloading should also happen properly. So you can see the loading here has to happen certain way. Loading here peak is good, but loading is not. Here loading is slightly, here loading is much better, then it goes away after certain point of time. So the gray area is the biofidelity corridor, comes from the cadaver testing. Now again, it comes from a cadaver testing. It doesn't represent a living human being. It represents a dead human being will have different material properties and the living human being. And we are trying to copy the dead human being because that's the data available. We can always approximate ballpark, and these cadaver testings were done really long ago, and even in today's time it will be very difficult to find an approval for these kind of tests. Rigor mortis happens and the muscle stiffens and material property changes, and you cannot make the dead body sit upright in the proper position like this position. So you have to hold them at certain point. You have to actually pressure the chest cavity for this kind of testing, so that it doesn't collapse directly, and it can sort of accurately represent the living human being. So lots and lots of assumptions and approximations are used in these kind of tests, and we try to replicate that in FE. So you can see here that hardware has its own challenges even in meeting, but then it is still doable. So we were able to give them lots and lots of feedback based on these kind of tests. You can see here this IR track. That is a mechanism that can measure the 3D displacement of the chest. This ribs, the gray lines, the ribs, and they are slanted downwards. The abdomen, upper abdomen, lower abdomen, foam, pelvis, so accurately, much more detailed it is representing the throw dummy as opposed to hybrid dummies. And this is the latest update, and it is being used in some of the NCAP regulations. But this is still under research. You know, lots and lots of research is still being done on this. So again, this kind of field, uh, it's very crucial in today's time, very cost effective and very useful. If you wish to go into this field, you will probably do a really great state-of-the-art analysis, and your work is possible that could lead to a really great impact in terms of the safety. Now the job opportunities, every OEM, every car manufacturers will have a crash analysis team, a safety team, occupant safety team. They will have a structural engineering team. They have to have. They have to pass their cars. It's law. It's required by them for the law. By the law. There are a lot of engineering consulting services like Autoliv, ESI, Humanetics, Satvan. They do a lot of this kind of projects for the bigger OEM. Some smaller projects the OEM they give out to this kind of consulting services. They do it for them. Autoliv develops airbags and seat belts. Humanetics develops this kind of dummy models, hardware as well as FEA. So FE has a lot of lots and lots of opportunities. There are crash test labs in India and abroad. They do physical testing, but they also do the virtual testing, FE analysis to just make sure that physical testing is done, because sometimes you just get a one chance of doing it right, and they will have their own. While doing the physical testing, you will have a lot of your own checklists. It has to follow certain protocol and all that, and it will be as rigorous as maintaining the temperature of the lab and the humidity of the lab. It will be that rigorous. There are universities and research labs that they do this kind of a work. So how do you enter in this field? You can study this. You can study crashworthiness and occupant safety. You can study biomechanics. You can learn skills like CAE analysis. You can learn meshing. So these are the mesh. They were done by us. The entire team. Each and every part we have hand meshed it. Each element, each node were meshed by us. It took us. It was a team of 6 people. It took us 6 months to develop this. And it will have its own quality criteria if you are aware of it. I think you must have studied FEA in your engineering courses. So you have to follow that. You have to maintain your time step. So you can learn that. You can learn different solvers like LS Dyna, PAM Crash, radios, Abacus, etc. So learning any one solver will be very helpful, because it's like a learning coding. One language, the other language will be easy, because the fundamentals are pretty much similar. It's just the usage of the terms might be different. It's the same thing here as well. You learn one solver, everything else will become easier. One of the most popular solver is LS Dyna. You can go to their website, you can check it out. They have a tool called LS Pre-Post. It's pre-processing where you can set up this kind of model, and they have post-processing where you have analysis done and you can just post-process it. You can analyze the data, etc., etc. It's for free. Anybody can download. You can just download it. It's very cheap. It's very small GUI based. They have some examples also. You can just download it, just check it out. What do you feel like it? Just have a feel of it. Very useful. So you can enter into industry after learning these kind of skills, become a CAE engineer. If you don't have, if you have learned a little bit outside, many of these industries, they will have their own training programs. Also, many of these standards that we see here, in addition to those standards, they will have their own standards, internal standards that they will want to follow, and they will have their own documents that what are the procedures, how to set up your model, how to position, in dummy like this, what is the procedure, which solver to use, what version of the solver, what version of the software to use, which software to use. They will have everything set up, so it's just matter of following it. You have to be a more resourceful, you have to be very intuitive in your analysis. So basics of your mechanics comes very handy here. Eventually your career path will become a senior CA engineer. Eventually you can lead a team, you can become a project coordinator, project manager, and so forth. So this might be a sort of a career path for you, possible career path for you. And now, very interesting topic. It's called future of safety. So what is the future of this field now? Now, as you all know, that there is a great push from the industry or from the government, actually, world government and all the nations towards hybrid vehicles or the electric vehicles, right? Because you want to be very sensitive towards the carbon footprints, and a lot of green initiatives are being taken by lots and lots of countries. So IC engine, it is possible that IC engine can become a thing of the past, at least in terms of road transport usage, for car and buses and etc. It is possible, and we are going in that direction. India is one of the four country in the forefront of this, that they are pushing for the electric vehicle, etc. But the safety is still going to be there. These standards are still going to be there, and they are going to become even more rigorous because we are going to go towards autonomous vehicles. So what you see here, this position here, you see here, this position, it's called a standard crash position. You always assume when you do a crash test, I'll show you a video after this. When you do a crash test, you just put your dummy in this position, that's all. But that's not accurate. You, me, anybody in the car, when you see a crash happening, you don't sit like this, like a statue, you move, So when you are going in an autonomous vehicle direction, it's even more evident that you are not going to pay attention what is happening, because car is going on its own, So you are probably sleeping like this, you can see here, you're probably sleeping like this, you are not in this direction, this position at all. That changes everything. That changes all mechanics, it changes all the load transfer to different parts of your body, So it makes safety scenario even more complex. You could be sitting in a car having a round table conference when crash happens. So everybody is in a different position. So how do you use this one particular standard to justify all the crash test scenario? You cannot, right? So it is going to become, so it is still state of the art. They have come up with an autonomous Thor AV, Thor models, Thor dummy models for AV, means autonomous vehicle. It is this one. It doesn't look much different, but it is different. It is slightly slanting position towards back, And now these hardware, they cannot stand up, they are these hardware. So this pelvis angle here, it cannot be straightened. You can straighten the lower legs, but you cannot straighten the upper legs. It will be in this direction only. You can only move lower legs and their arm. That's it. Not more than that. Yeah. So this is a state-of-the-art model because it incorporates little bit of thorax angle. There is a pitch angles here. You can change the pitch. You can, but it's very little. It cannot be sleeping position. It cannot be. If you want to do it, you have to change your entire hardware. You have to change the spine, you have to change the pelvis, you have to change the abdomen. You know, so first thing the industry would want to come up with is a hardware that can be positioned in any position, but that will be very difficult to certify that hardware. So this is state of the art. They are working on it, but now, but this is just about the hardware, right? Hardware has limitations. You cannot use cadavers, and you have to come up with the hardware, and you will come up with it. But virtual doesn't have that limitation, right? Virtual, you can do anything. So instead of using the FE model of models of these hardwares, what you can do is you can take a human being, put them in the MRI machine, take all the images, uh, create all the CADs, mesh them, and you can have an actual human skeleton like this. You can see here, like this one. This is the CAD model, like this one here. This is the FE model of the same CAD, So you can use this, right? So this is called human body models. This model here is called, it's GHBMC, uh, Global Human Body Model Consortium. And they have developed this model, extremely state-of-the-art, very, very detailed model. The rib cage, sternum, the lungs, the heart inside, the aorta, the liver, the stomach, the intestine, and the pelvis. You can see here, pelvis, the pelvic cavity. It's so detailed. The brain is, oh my god, its brain is extremely complex and detailed. And again, I have been very fortunate in working on the head model of this particular GSBMC model, because I was studying at Wayne State University and they were part of this consortium, and head was developed at Wayne State University, and I was one of the lab assistant who worked on the virtual head model. And so it's extremely complex. All the material, getting the material data for each and every body part is very difficult. It's very dark side of the research, and it's very difficult to come up with a stable material model. LS Dyna is working on this. A lot of universities are doing research on it, and lot of all the OEMs, they use human body models. Toyota has its own human body model called thumbs, widely used in industry, and this human body model is also a thing of past. So we have gone one step further in that as well, So what they have done is that these human body models have modeled these muscles, the red muscles that you see here, and these muscles, they have modeled such that they are active. So meaning, when you push them from behind, they can push back. If you push them from behind, they can straighten up again. It can calculate its own internal force that it's required to push back based on the external forces, and that is being used in the active safety part. The human is doing a lot of maneuvers, swerving and pushing, and that is, so this is the new direction, integrated safety. One model that can go from active safety to passive safety, it can do all the maneuvers, it can have all the muscle activations based on the boundary conditions, and then safety system kicks in, and you have your injury criteria fulfilled or not, etc., etc. So yeah, so basically this is the field, extremely complex, extremely state of the art. From dummy, which is the hardware limitations, they are also going state of the art. In the virtual direction also, human body models, they are also going in a different direction. Again, I was fortunate to work on active side of human body models with the muscle activation when I was working for Mercedes-Benz in Bangalore. I developed one of the first model for them with that active muscles. So let's just watch one crash test video, and let's just look at it from this perspective of crashworthiness, how certain parts of the car has to crumple, and let's look at how the hardware inside will behave, how airbag comes in, how it helps, Let's just take a look at it. Now this is from YouTube. Okay, you can find thousands of crash test videos. This is off-road Mitsubishi Outlander. It's called. I am not sure. Outlander. Sorry, yeah, Mitsubishi Outlander. And this is the front crash scenario, the simplest front crash scenario. And these are two dummies sitting inside. You can see here. Now their faces are painted because when they go and impact the airbag, they actually want to go back and see where exactly there was a contact on the airbag. Based on the color, they will leave the imprint on the airbag. You know. So yeah. So let's just take a look at it. They will show it from different angles. So you can see the crush here of the front part of the structure, and if you can see the time frame here, it's very less. Time frame. Check out this time frame here. So they are literally getting up from their seat. You know, the pelvis is leaving the seat. That makes it very complex scenario. So let's take a look at the chassis and the front part from the bottom view. And you can see that how at the contact it starts crumpling here. Here, you see, it's not even pretending to withhold, to maintain the strength. No, it's crumpling right away. And you see this is the fuel tank. It has to be protected properly. So this car, the positions of everything is designed so accurately and with so much research, so it has to crumple, it has to take away that load from the occupant. If that doesn't happen, that load is going to go on the occupant. So yeah, this is the actual physical crash test. The number of crash tests happens that it's very low, and when this happens, they take a look at this one video 100 and 200 and 300 times. They just exhaust every angle, every view. You can imagine how many cameras are there. What is the frame rate here? 1000 frames per second is the frame rate. So you can imagine, right? So much data is generated, and it's not easy to keep on repeating this test again and again. So every time you do these tests, you have to make sure that you do such tests in such a way that you get maximum out of it, because it's very expensive. There's an entire team sitting around, not just one or two person, an entire team. One will be setting up the car, one will be setting up the dummy, one will be setting up all the sensors, all the instruments, one will be setting up all the cameras and everything, one will set up the data acquisition part, how data is collected, which channel is collecting from where, what is the signal that it is connecting, how to process those signals. It's huge. It's a task in itself. It's a field in itself. So yeah, and you try to replicate this in FE. FE, it's much more easier because it's easy for you to manipulate, because you can just say, I want acceleration of this node very easily. You don't have to do the instrumentation part of it. But yeah, so one simulation you exhaust all side of it. You do lots of rigorous analysis. You check all the forces, accelerations, you make sure all the energies are accounted for, and you can try to make sense of it, why it happens and how it happens. And that is one of the major skill. Software skills at some point can be acquired easily. It just requires training. But analytical skill is something that you have to be intuitive. You have to have your basics very, very clear, very well understood. That will help you go a long way in your career.